Okay, in this problem set, we're going to continue talking about exponents and look at some exponent rules. So recall when you have a base like 2 to the exponent 4, the exponent tells you how many times the base is multiplying itself. So 2 to the 4th is 2 times 2 times 2 times 2, which is 16. So in general, the definition, if you have a base like x to the exponent n, the exponent tells you how many times the base is multiplying itself. Or you could say the exponent tells you how many factors of the base is multiplying itself. So x to the n means you have n factors of x multiplying itself. So x to the third would be 3 factors of x, right? X times x times x. X to the 2 would be 2 factors of x, x times x. So what would x to the 1 be? It would be just 1 factor of x, wouldn't it? So that's why you can say rule 1 here. When you have x to the first power, it just means x. Anything to the first power is itself. Okay, so we're going to use these that fact in just a minute. But let's develop a more useful rule here. X to the 3 times x to the 2, let's see, if you just look at the definition in product form, doesn't this say you have 3 factors of x? Doesn't this say you have 2 factors of x? So if you want to write this in exponential form, does that mean you have 5 factors of x? So can you see what the pattern is? X to the 3 times x to the 2 is x to the 5th. Let's try one more, then we'll look at the rule. W to the 4th says you have 4 factors of w. W to the 2 says you have 2 factors of w. So if you add them up, or the total number is 6 factors of w, so in exponential form that would be w to the 6th. So do you see the pattern? Yeah, when you're multiplying, the pattern is, when you're multiplying two numbers with exponents, and the bases are the same, they must have the same base, and you must be multiplying, then what you could do is a shortcut. You could keep the base the same and add the exponents. That's what this rule says. So when you have like z to the 3rd times z to the 4th, since you're multiplying and the bases are the same, you just keep the base the same and add the exponents. It's a shortcut. Alright, now how about this one? What about x to the 5th times x? Now remember, x is the same as x to the 1. We just talked about that. That's rule number 1. So x to the 5th times x is the same as x to the 6th. Now it's crucial that the bases must be the same. For example, if you have like z to the 3rd times y to the 3rd times z to the 4th, since the bases are the same, there's absolutely nothing you can do to this. You just got to leave it as z to the 3rd, or y to the 3rd times z to the 4th. Furthermore, it's crucial that you must be multiplying. If you're adding, you can't use that rule we just talked about. The rule only works when you're multiplying. So I guess what can you do? Well, it turns out there's nothing you can do to this, and the reason is because you're adding and they're not like terms. You see, like terms have to have exactly the same variables to the same powers. So this has y to the 3rd, this has y to the 4th. You're adding, they're not like terms. Can't do anything, just got to leave it as that. Let's continue talking about that issue for a minute. Let me go back. When you have like terms, like go back to here for a second here. So, suppose you have like 7x plus 5x back in chapter 1. Like terms mean the variables are exactly the same. Remember how you do it? When you do have like terms, you add the coefficients, and you leave the variable the same. You don't do anything to the variable when you're adding like terms. You just add the coefficients. So in this one right here, these happen to be like terms because you have exactly the same variables to exactly the same powers, and you're adding. So you do it the same way. The answer is going to be 7y to the 3rd. Notice how you keep the variable the same when you're adding. These are not like terms. 6x plus 5x cubed, so you just got to leave it as 6x plus 5x cubed. Here you're multiplying, and the way you should think of this is negative 3 times y to the 5th times 5 times y to the 2. Since you're multiplying, you can use the commutative law, and you can multiply the coefficients. What's negative 3 times 5? That's a negative 15. And then, since you're multiplying and the bases are the same, here you can add the exponents. So the answer would be negative 15 times y to the 7th. This one, you're multiplying, the bases are the same, so you can use rule 2. And so this is x to the 1, right? So it's x to the 3 times x to the 2 times x to the 1. If you add all the exponents, you get x to the 6. Alright, here's another rule. Rule 3. We'll look at this in class a little bit, but it turns out anything to the 0 power is 1. Don't get it confused with rule 1 that says anything to the first power is x to the first power is x. This says x to the 0 power is 1. We'll talk about why this is true in class. So what's 5 to the 0? Anything to the 0 power is 1, so it's 1. What's 1,245 to the 0? Well, it's something to the 0 power, so it's 1. Of course, you got to be a little careful here. Remember this issue. The base of this exponent is really not negative 3, it's just 3. This is actually equal to negative 1 times 3 to the 0. So the base is 3, so 3 to the 0 is 1, but this is negative 1 times 1. The answer is negative 1. That came up earlier, didn't it? Here the base is actually negative 3. So here it's equal to 1. See the difference? Well, let's do a few more. What's the base? The base here is negative 3 fourths. So this is just something to the 0 power, which is 1. Here, this is really tricky. The base of this is actually 3. Remember, you can think of it as negative 1 times 3 to the 0 over 4. There's no parentheses. So the order of operation says you do the exponent first. So it's just negative 1 times 1 over 4, which is negative 1/4. Okay, we'll do a few more, then I'll give you some to try. How about that? Alright, so let's look at these. Here you have negative 5 x to the third times y to the 0. Well, there's not a whole bunch you can do to this, except y to the 0 is 1, so we usually don't write our answer like that. Just leave it. Since you're multiplying by 1, you don't have to write it. Just leave it as negative 5x to the third. Okay? Here we go. Now this looks really hard, but it's actually not. Since you're multiplying everything, you can literally think of this as 3 separate problems here. You can multiply the coefficients. What's negative 2 times negative 5? That's just negative 10, right? Now with the x's, since you're multiplying and the bases are the same, x to the 2 times x to the 4, yes, you can add the exponents there. So you get x to the 6. And this is, remember, this is y to the 1 times y to the 3, so you get y to the 4. You can do it all in one step, pretty much. Well, alright, go ahead and hit the pause button and we'll visit this a second. Okay, on this first one, you're multiplying, and the bases are the same, so yes, you can use your exponent rules. You multiply the coefficients first, so 5 times negative 3 is negative 15, and you can add the exponents, so you get x to the 7th. Here, you are adding, or you could say subtracting, adding the opposite, but they're not like terms because the exponents are different, so there's nothing you can do to this one. Okay. This one, you have something to the 0 power. Now the base is negative 3x, so this is just 1. This one, the base is actually, what? The base is x. So since there's no parentheses, x to the 0 is 1, so this is negative 3 times 1. Let's see, on this last ones, you're multiplying 4x squared times 9x squared. You can multiply the coefficients together and get 36. You can add the exponents and get x to the 4th. Now, look at this last one and compare this last one with the one you just did. When you multiply and the bases are the same, you add the exponents. When you add and they're like terms, which means the variables have to be the same and the exponents have to be the same. So these are like terms. But when you add, you do not do anything to the exponent. You leave it the way it is. All you do is add the coefficients. So look at the difference between number 24 and 25. All right, that'll just about do it. We'll see you later. Bye-bye.